So stepping back now and just thinking about our simple ocean model as a reservoir for water. We have input fluxes of a whole range of elements into the ocean, and we have the output fluxes from the ocean, and generally to sediments. In this diagram here, we've named the input fluxes. We've given them the symbol R, signifies river, but there are other inputs as well. And then we have the losses as S or sediments. Most of the input fluxes are zero-order processes, so they aren't dependent in any way on the concentration of the elements in the ocean. But as we discussed in the cycles lecture, most of the output fluxes are actually dependent on the concentration of a particular element or ion in the ocean, and as a result are a first-order process or follow first-order kinetics. At steady state, we have an equilibrium here between the input and the output fluxes, and the inputs would equal the outputs of a particular element, and the concentration of an element in the ocean wouldn't change with time. Unfortunately, we haven't been able to measure the ocean for long enough to really understand whether element concentrations are changing with time or not. So let's just have a look at the composition of river water entering the ocean with the view to trying to work out what the residence time of different salts are in the ocean. So here is some data for dissolved ions in river water, and these are the percentages by weight of the total salt content of the river water. You'll notice down here the average river salt concentration is 0.120 per mil as opposed to 35 per mil. So there's a lot less dissolved salt in river water, which shouldn't come as a surprise because it's mainly fresh water. Now, if you actually have a look at the composition of some of the major salts in seawater compared to river water, so here we have our river water. These are the concentrations here in milligrams per litre. So we can see that the river water is dominated by this ion here, which is a bicarbonate ion, or HCO3-. And it has significant amounts of sulfate, silicate, and calcium, and lesser amounts of chlorine, sodium, potassium, and magnesium. Now compare that to seawater, and we can see, as we've noted before, the sodium concentrations and the chlorine concentrations are much higher with lesser sulfate. The relative concentrations of the salt entering the ocean is very distinct from the actual composition of the ocean itself. And those differences really reflect the residence times of the elements in the ocean. Before moving on, you might just note that here is rainwater, and you'll notice that rainwater looks very similar to what it is in the ocean. And that simply reflects when we have evaporation of water from the ocean, and when it's combined with salt from sea spray, then rainwater itself ends up looking very much like the seawater, albeit much fresher. It contains the signature of the original source of the ions, which is from the ocean itself. I've just summarised that there. So now, taking those river water concentrations and also knowing the concentrations of ions in the ocean, we can calculate the residence time of salt constituents in the ocean. So if we make the simple assumption that the ocean is steady state, we can either use the river ion inputs or the sediment outputs to make the estimate. Both of them have shortcomings because it isn't just rivers, it includes a number of other inputs that we've discussed. And similarly with sediments, it's very difficult to actually make a good estimate of the composition of sediments that are due to removal of salts from the ocean. So here we are, we're going to use the rivers. And so the residence time of an element, tau, is going to equal the amount of that element in the ocean divided by the river flux into the ocean. To make the calculation, we use the concentration of a particular element in the ocean times the mass of the ocean. So that gives us the total amount of that element in the ocean. Then we have to divide that by the river flux into the ocean. So to calculate that, we need the concentration, the average concentration in rivers entering the ocean. We have to multiply that by the mass flux of water into the ocean each year. So those numbers are actually down here. This should actually say the mass of the ocean rather than the volume, which is 1.35 times 10 to the 21 kilograms. And the river flux of water each year is the mass of water in the rivers that enters the ocean every year, and that's around about 3.74 times 10 to the 16 kilograms per year. So combining our concentration of element A, these square brackets represent concentration. There's a concentration in the rivers, this value here. They're in this column here. We have the concentration in the ocean. So the element A, square brackets, gives the concentration in grams per kilogram in the ocean. And that's these values here. You can see that these are much smaller values than these in grams per kilogram. And then we multiply these concentrations by the mass and the river flux, mass of the ocean and river flux respectively, and do this calculation. And we come up with numbers like this. So for chlorine, 130 times 10 to the 6 years. So 130 million years is the average time a chlorine ion spends in the ocean. It's slightly smaller for these other salts, but you can see they're all really quite significant. The smallest here above this line range between 1 and 130 million years. Bicarbonate ions, unlike these ions, it has a shorter residence time, so this 0.1 times 10 to the 6 is 100,000 years. And in the case of silicon, which the glass sponges and the diatoms use, we can see that it actually has a much shorter residence time, 0.02 times 10 to the 6 or 20,000 years. Now, just a final note here about using these residence times, and this is sort of interesting when we start looking at chemical oceanography, is that all these elements or ions that have residence times greater than 100,000 years, they're known as conservative elements in the ocean. So they have long residence times compared to ocean mixing time. So the average time it takes to actually mix the whole ocean for one mix or one cycle is around about 4,000 years. So you can imagine if you had some salt in a cup of water and you spun it around once with a spoon, it wouldn't mix thoroughly. But if you were able to spin your spoon 25 times, that salt would then end up very well mixed. So 100,000 years is roughly 25 cycles, and that results in very uniform mixing of an element with a residence time longer than 100,000 years. Those elements end up being very well mixed or uniformly distributed in the ocean. Elements with shorter residence time, like silicon or manganese, aluminium or iron, which has an extremely short residence time, these are known as non-conservative elements. This should say short residence times compared to ocean mixing times. So they're poorly mixed, highly variable distributions in the ocean. So there we go. That's really the end of our exploration of salinity. And so through this lecture, these are the main topics that we've covered, and I'll leave you to look through each of those.